A planet of mass m is attracting a very tiny object of negligible mass small m. Let's say at time t equal to 0 that small m is at rest, and right now it's at a distance of Ri, r initial, from the center of the planet. The center of masses are at a distance of Ri. Now, as time passes by, what's going to happen? Well, it's attracted and there are no other forces acting. Imagine that this is in vacuum. Then it'll accelerate towards the mass, right? It'll keep accelerating, its velocity will keep increasing, and eventually, after some time, it'll come somewhere over here. Let's call that distance to be RF, the separation distance at the final point of our interest. The question that we want to try and answer in this video is, when it's over here, what is its speed going to be? Our goal is to find an expression for the speed in terms of Ri, Rf, the masses, and the appropriate constants. So, how do we do this? Well, one way is to use Newton's second law. If we know what the net force is, and here there's only one force acting on it, the force of gravity, we can use that to calculate acceleration as a function of time. And from acceleration, I can calculate the velocity as a function of time, and then I can use that function to figure out the speed at this particular point. But that's going to take slightly longer. So we're going to take a slightly different approach over here. We're going to use the work-energy theorem. Okay? So remember work-energy theorem? It says that the change in the kinetic energy of an object will always equal the total work done on that object. We're going to use this to try and calculate the velocity over here. Okay? All right, so let's do this. What is the change in the kinetic energy? Well, it's the final kinetic energy minus the initial kinetic energy. So that'll be the total work done. What is the final kinetic energy? Well, the final point is over here. This is what we are interested in. So the final kinetic energy is half m into v squared. We don't know what v is, right? So we can just call that as half mv squared minus what's the initial kinetic energy? Initial kinetic energy is this point. This is the initial point. Well, it's at rest, so initial speed is 0, so initial kinetic energy is also 0. So you get minus 0, and that equals the total work done on this tiny mass. And so now the big question is, how much is the total work done? How do we figure this out? Well, just to recap, remember, work done by any force is given as the dot product of the force and the displacement. So to find the total work done, we have to find the work done by each force acting on this mass from here to here, and then just add them up. But there's only one force acting on our object, right? There is only the force of gravity acting on an object. So the work done by gravity will be the total work done. And so the main question now for us is, what is the work done by gravity when the mass comes from here to here? So here's my attempt, okay? So the work done by gravity would be the force of gravity times the displacement times the cos of the angle between them. So what is the force of gravity? Let's just call it as Fg. And what is the displacement? Well, the displacement is from here to here. So that's Ri minus Rf. So its magnitude is Ri minus Rf times cos of the angle between the two. What's the cos of the angle between the two? What is the angle between them? Well, the force is towards the left. And the displacement is also towards the left. So the angle between them is 0, so you get cos 0. Cos 0 is just 1. And there we have it. That is the work done. That's my attempt. The question for you is, do you think this is accurate? I want you to pause the video and think about this. Well, let's see. This expression for calculating the work done only applies when the force is a constant over the entire displacement. So the question for us is the force of gravity a constant over the entire displacement? And the answer is no. We know that farther away, the force of gravity is smaller, it's weaker. But as we go closer and closer, the force of gravity increases. So clearly, we cannot directly apply this expression. This is wrong. Okay, so what do we do? Here's what we can do. The force of gravity keeps increasing as I go from here to here, right? How about we divide this entire displacement into, say, 5 equal parts? And let's assume that the force in each section is a constant. Now, sure, even within the section the force varies, but it won't vary as much as it does over this entire displacement. So we can approximate, we'll take some approximate average value, and for each section, let's assume the force to be a constant. Then we can calculate the work done in each section separately. Here's what I mean. So let's divide this displacement into 5 equal parts. Let's call each one as delta R. Now what we can do is we can calculate the work done in this section as this force multiplied by this displacement multiplied by the cos of the angle between them. That is, the angle is 0 because they're in the same direction. So it's just going to be F times delta R. And it'll give me some value of work done for this particular section. And then I'm going to repeat over here. I'm going to calculate the work done in this section separately. It's going to be slightly larger than here because the force of gravity over here is slightly stronger than over here. And I'll just repeat, and then I will add all of them up, and that would give me the total work done. So when the force is varying, in general, our strategy is going to be like this. We divide the displacement into some number of equal parts, and then to calculate the work done, what we do is for each section, we calculate the work done individually by multiplying the force in that section and the displacement. So we take the dot product of the force and the displacement in that section, and then we repeat this for each section, and then we add them all up. In other words, we take a summation. That is how you calculate the work done when the force is varying. But this is not accurate, isn't it? Because remember, we assumed that the force is a constant in each section. It's not. The force is varying even within each section, right? So what we have gotten is an approximation. And just to make this point clear, we can also look at this geometrically. If you plot a graph of the magnitude of the force of gravity versus the distance r, where r represents the distance from the center of mass of this planet, then the magnitude of the force of gravity, as you go closer and closer to the planet, increases. This is how the magnitude of the force of gravity increases. And if we now consider the work done between some initial and some final points over here, then that work done geometrically represents the area under this curve. And the question is, how do you find the area under this curve? Because it's not a standard shape. Well, what we can do is we can divide this shape into, say, 5 equal parts. That's exactly what we did over here. And then approximate each part to be a rectangle. And then we can find the area of each rectangle individually, which is basically height into width. Over here, the width represents delta R, and the height represents the force at that particular location. And so you can see clearly over here, in each section, we're approximating the force to be a constant, but of course the force is changing. And so when we sum it up, we get an approximate value of the area. It's not exact. As you can see, there are some gaps over here, and there are places where we have overshot. So this is the approximate answer. But now comes the question, how can we make this approximation better? I want you to pause the video and think about it. Well, instead of 5 parts, divide this entire section into 10 equal parts. Now notice, you will get a much better approximation. So you see where we're going with this. The more number of parts you divide it with, the smaller the delta R you choose, the better your approximation becomes. And then eventually, under the limiting case, when delta R is approaching 0, our approximation approaches the exact value. So technically, the work done would be equal to this summation under the limiting case when delta R approaches 0. And we call this the integral. And of course, the integral will have some bounds from some initial position to final position. Such integral in which a function is evaluated over a specific path. We give a name to it, we call it a line integral. So work done is most fundamentally and generally defined as a line integral. But of course, when this dot product between the force and displacement is a constant over the entire path, well, it simplifies to give us this expression. So coming back over here, what's the work done by gravity? Well, it's going to be the line integral of fg dotted with dr along the object's path. And what are the bounds? The lower bound is the initial position ri, and the upper bound is the final position rf. So that simplifies to the left-hand side becomes half mv squared, and now we need to evaluate this integral. So let's clean things up a little bit. Okay, so we have two things that we need to figure out. What is the force of gravity vectorially? Well, for that, we can use Newton's universal law of gravity. An object at any distance r from the center of the mass of a planet will experience a force of gravity, which is given by, in magnitude, it's going to be the constant g times the product of the masses divided by the square of the distance between the center of masses. Okay, so that's the magnitude. But what about its direction? Well, notice the direction is, well, it's attractive. So the direction over here is to the left. But how do we write that vectorially? Well, we can say that the direction is in the opposite direction of my position vector r, right? The position vector is from the center of mass of the planet to this point. So the direction of the force is in the opposite direction. But how do I write that vectorially? We write it as negative r hat. R hat is a unit vector, meaning its magnitude is 1. And that vector will be in the direction of the position vector over here. So since our direction is to the left, we'll use minus r hat. And since its magnitude is 1, it doesn't add anything to the magnitude. So it's only useful to represent the direction. So this is the vector expression for the force of gravity. So we have this. Okay, next we need the vector expression for the displacement dr. How do we represent this? Remember, dr is an infinitesimal displacement, right? How do we represent that? Well, again, vectorially, dr would be equal to the magnitude of the displacement, which is just going to be, we'll just write it as dr, times the direction. And the direction, we can use, again, r hat to represent the direction. But what will be the direction? Will it be in the positive direction or the negative direction? That's the important part. Well, I should think, hey, this object is going from, it's moving towards the left, so its direction should also be negative r hat. But that would be wrong because the direction of the displacement is taken care by the bounds. Since I've already input the bounds as ri to rf, that takes care of the direction. And therefore, I don't have to think about the direction over here. I'm just going to multiply it by r hat. Does that make sense? What I mean to say is we don't have to worry about the direction of the displacement over here, because it's being taken care by the bounds. For example, in our case, to represent that the object is going closer to the planet, look, the lower bound is a bigger number compared to the upper bound. If we wanted to represent the object going farther away from the planet, the lower bound would be a smaller number compared to the upper bound. Does that make sense? So it's the bounds that take care of the direction of the displacement. So we don't have to worry about the displacement direction over here. Okay, so we have both of them. We can plug this in. So it's going to be the integral of the force, which is this thing over here, dot their displacement vector, so which is over here. Okay, let's simplify this. So what do we get? Well, dot product only applies to vectors. So we can separate out the magnitude. So minus g mm by r squared times dr. We'll separate that out times the dot product of r hat and r hat. What's this dot product equal to? Well, remember, dot product equals the magnitude of r hat, which is just 1, times the magnitude of the other r hat, which is also equal to 1, times the cos of the angle between the two r hats. Well, the two r hats are in the same direction, so the angle is 0, so cos 0 is 1. So it's 1 times 1 times 1, which is 1. So this dot product is just 1. We're done with vectors. We're only left with the magnitudes now. Okay, so what will that give me? Well, I can pull the constants out, minus g mm, I'll pull it out, and I'll be left with the integral of 1 over r squared dr. Okay, what is the integral of 1 over r squared dr? Well, that's just negative 1 over r. And of course, we have the bounds over here. Well, from here, we just have to simplify. So it'll be a great idea to pause and see if you can derive the expression for the speed yourself. Okay, so the minus sign cancels out. And so now I can plug in the bounds. We first plug in the upper bound minus the lower bound. So I'll get 1 over rf minus 1 over ri. The masses cancel out. And from here, v squared equals rearranging 2 times this thing. And if we take square root on both sides, I will find my v to be the square root of 2gm into 1 over rf minus 1 over ri. We have found the expression for the speed at this point. So the final thing we need to do is make a sense check over here. First of all, does it make sense that m is not a part of our equation? Yeah, because we have seen before that the acceleration of an object due to gravity is independent of its mass. And so the speed it would have gained is also independent of its mass. We also notice if the mass of the planet increases, then again the speed increases. That makes sense. If this was a much more massive planet, the force of gravity would be much stronger, there'll be much more acceleration, and so this speed would be higher. Another thing you can notice is that if Ri was the same as Rf, if these two values were exactly the same, then this will give me 0 and the speed would be 0. Does that make sense? Well, yeah, if Ri equals Rf, then notice its position has not changed at all, which means it's at time t equal to 0 itself, and the object is at rest, so its speed is obviously 0. Another check we can do is, what if Rf becomes larger? Well, then this number becomes smaller, and so the speed also becomes smaller. Does that make sense? Well, yeah, if Rf becomes larger, then we are letting the mass only accelerate for a smaller distance, and so it wouldn't have gained as much speed as before, so you would expect the speed to be lower. That makes sense. And look, what if Rf was larger than Ri? Then this number becomes smaller than this number, giving you a negative number under a square root. What does that mean? Well, if Rf is larger than Ri, we're asking what is the speed when the mass goes farther away from the planet? And that's impossible. When an object starts from rest, it'll always be attracted towards the planet, and so it'll only move closer to the planet. It can't move farther away, so it's basically saying that situation does not apply over here. And finally, you can also check for the units and make sure the units on the left is the same as the units on the right. That is something that you can try yourself. Finally, before we end the video, I want to talk about a cool application of our hard work, something that blew my mind when I first saw it. Ready? Okay, we can use this to estimate the speed at which an asteroid can hit a planet. Here's how we can do it. Let's make a copy of this, okay? So if an asteroid were to come and hit our planet, what would be the positions Ri and Rf? Well, Rf would be over here, so it would be just the radius of the planet. So for Rf, we'll plug capital R, which is the radius of the planet. What would be Ri? What would be the initial position of the asteroid? Well, an asteroid very, very far away would make Ri to be very large. If Ri is very large compared to the radius of our planet, then this number is going to be very small compared to this number. So we can just neglect that. And there we have it. This is the speed at which an asteroid would hit a planet. And notice that only depends on the mass of the planet and the radius of the planet. Now, to be clear, we're assuming that the asteroid starts at rest from very far away. But that need not be true. The asteroid could be moving towards our planet already from far away, which means the speed could be higher than this. In other words, what we have found is the minimum speed at which an asteroid could hit a planet. I find this incredible because if I know the mass of a planet and the radius of the planet, I can actually find a value. Let's do that for Earth. If we plug in the mass of the Earth and the radius of the Earth, this number comes to be approximately 11 kilometers per second. So as mind-boggling as it sounds, just by sitting over here at our desk using a pen and paper, we can calculate the speed at which, the minimum speed at which an asteroid could hit the Earth. That's incredible, right? Now, of course, there are some nuances. If the asteroid is very tiny, then when it enters our atmosphere, it gets slowed down or it can even just burn up. But of course, if the asteroid is large enough where the slowdown effect is much negligible, then this is a very good estimate of the minimum speed at which asteroids could hit our planet. And here's the final thing that blows my mind. Are you ready? If this represents the minimum speed with which an asteroid very far away would come and hit a planet, the reverse must also be true. This is also the minimum speed at which you should launch an asteroid or any object, for that matter, from the surface of the planet so that it can go very far away. In other words, it can escape the planet's gravitational pull. And therefore, this is also the escape speed of the planet. And so the escape speed from the surface of the Earth is roughly about 11 kilometers per second. Again, ignoring the effects of atmosphere. This is an important number if you are working with rockets and spacecrafts.